And welcome, grade 10s. Today we're going to do our last session on wave, sound and light, and we're going to look at the electromagnetic radiation. Now, this is a really nice section. It sort of isn't sound, it is definitely not sound, and it's sort of light but not quite. And what we're going to do is we're going to look at the fact that electromagnetic radiation is actually really important. You just don't experience most of it. That you think you're not experiencing it. Light is such an important part of the spectrum. And what we're going to look at today is we're going to look at some key things that are important. And number one, we're going to look at the properties of light. Light is a very, very important part of the electromagnetic radiation. We're then going to look at the wave nature, or the wave-like nature of light. And this is a bit of a debate between scientists that has been going on for 300 years. And I'm not sure it's ever actually going to be ended. I don't think anyone's ever going to make a complete decision as to what light really is. But we are going to look at the wave-like nature of light and why we think it is that. We're then going to look at the electromagnetic spectrum, of which light is a very small part. Then we're going to have to look at the penetrating ability of the electromagnetic radiation. In specific, we're going to look at UV radiation. You all know about UV radiation, and you all know, especially with global warming and everything else that's going on in the hole in our ozone, that we need to be using things like sunblock and sun cream to stop us from getting things like skin cancer. And you know, it doesn't actually matter what the pigment of your skin is. That's a very important thing to consider. So we're going to look at those sort of things and why UV radiation actually burns us. Then we're going to look at, when we end today, we're going to look at the particle-like nature of EM radiation. And in fact, light also has a particle nature. And we're going to discuss a little bit why we think it has that particle nature. Unfortunately, for you in grade 10, we don't look at the experiments that actually define particle nature for us. But we are going to hopefully explain it a little bit more for you so it makes a little bit sense. So that's where we're going to go. So let's just jump right in there and talk about the special properties of light. Now, light, you've dealt with lights, okay? And we're very grateful we have light, especially in the morning when we wake up. It's where summer's really nice because we have early mornings. You don't have to wake up in the dark, which is really horrible in winter. But we have these early mornings, we go outside, and we can see the world around us because we have light that comes from the sun. At home, we all know what it's like to experience a blackout where we don't have electricity for whatever reason, and then we have to study or work by candlelight. We know that's just not fun, but we can still do it because we have light. So light's a really important part of our lives. I'm hoping you also all realize, after a rainstorm, the most prettiest thing to see is when we see a rainbow in the clouds or through the sun, and they're actually really pretty to see. And what that rainbow is showing us is the spectrum of colors, which are red, orange, yellow, green, blue, indigo, and violet, which you don't need to know. But we have that beautiful spectrum of colors, and that is part of what we call the spectrum of light, where we can separate light into these beautiful colors. Think about when you go to the paint store and you've decided you want to repaint your bedroom, and you don't want just a normal shade of pink or blue or purple. You go to the paint store and they mix a brand new shade of color for you. And you go, oh, that's exciting, because only your room would have that color, and your mom and dad are probably going, do we have to? But it's okay, you're a teenager, you're allowed to. But we have this huge spectrum of colors. Think about when you go to the shops to do clothes shopping, or every season, especially for the girls, there are different colors that are in. And in fact, at the moment, the colors that are in are neon and bright. And as part of the older generation, I struggle with those. But hey, you guys like it, and everything glows in the dark. And that's all part of the spectrum. It's all part of this huge color spectrum that we get. But that's not all that's special. So by spectrum, we're talking about the colors. And here, I'm really talking about visible light, the stuff I can see. Even on our set, you can see a whole bunch of different shades of blue behind me and the red for the X. So it's great, we like that. But what about the speed of light? Now, this is actually a little bit of a debate at the moment in the scientific community. The speed of light is always been considered to be the maximum speed that anything can travel at. And it's specifically 3 times 10 to the 8. Now, that has been the ultimate speed of light. When you watch sci-fi programs and they talk about traveling through the universe, they often talk about traveling at speeds greater than the speed of light, which is what makes it science fiction. The honest truth is no one really knows what would happen to the human body or matter if we should be able to travel at the speed of light, and that's what Einstein was talking about with his famous equation E equals mc squared. But at the moment, there really is a debate in the scientific community as to whether they've discovered a subatomic particle, a particle inside the atom, that is traveling faster than the speed of light. Huge debate. This is going to turn the scientific community on its ear. So everything's going to get turned upside down if they find that it really is. But for now, we're going to say this 3 times 10 to the 8 upper limit, excuse me, of anything. Nothing can travel faster than the speed of light, which is still incredibly fast. Okay? Then, now we get to the fun part. Light has a wave nature. What does that actually mean? Well, waves are, think about ocean waves. We have our waves coming, they're crashing along the sea. When you watch waves come in through the ocean, I'm sure you've noticed the wave changes, and the wave gets refracted, its speed changes. We can only do that with waves because they're continuous. Okay, and the wave comes along and now it's losing depth and can't go as deep as it was, so it changes its speed because we change its wavelength. Okay, we can't change its frequency. Frequency is set by the source. So the wave's wavelength changes, so its speed changes. But only waves do that. Reflection. You see reflection, think about it, in the morning you get up, you have your bath or your shower, you decide you need to look good for school, and it's very important, you brush your hair, you brush your teeth. You do that in a mirror. We do it in a mirror because we can see a reflection of our image, which is actually quite important. I like being able to do that in the morning, just make sure everything's in place. The reflection means that the light that comes to me gets reflected off me onto the mirror reflects an image back to me, which I can then see. That's because it's a wave, all right? And not only do we get things called diffraction. You're not going to do diffraction too much this year, but with diffraction of light, what that means is the light can spread out. It goes through a little gap and it spreads out. For example, you're driving in a car at night and you see headlights coming from the car coming towards you, and through the windscreen it looks like the headlight gets all fuzzy. It's not a nice little round dot from the headlight, okay, but it gets all fuzzy. That's because of diffraction, okay. Now that happens because light has a wave nature, but at the same time, light is also what we call a particle. It has a particle nature. For example, how do I know it can have a particle nature? Think about a squash ball. Okay, when you play squash, you take a tiny little round rubber ball and it gets hit against a wall. When it gets hit against the wall, it bounces back off the wall. That is a form of reflection, because that's what's happening when a wave gets reflected. It's bounced off a surface. That means that now we have this situation where, well, light definitely behaves as a wave, but then it could also be a particle because it can also be reflected. Okay, particles, refraction can't happen as much, but for example, a good place of where we could see refraction is in a crime lab. I'm sure you've all seen programs like CSI and that sort of thing, where they test fire a gun. When they test fire a gun, they shoot the bullet into a container of water or into a special gel. Now, the nice thing is when you watch it, they film these really nicely, is you see the gun slow down. Not the gun, sorry, the bullet. The bullet slows down as it gets into the water or through the gel. Now, what's actually happened there is we've changed the speed of the bullet. That is refraction. We've changed its speed. That means this particle has been refracted. So if light can be refracted, then that means it can also be a particle. And this is where the debate is. The honest truth when it comes to this, grade 10s, is we cannot set up experiments where we can 100% prove it's a wave or a particle at the same time. We can either do an experiment to show that it's a wave, or we can do an experiment to show that it's a particle, but we can't do both together. So scientists have really come up with this and said, well, you know what, for now, we're going to say that light has a dual nature. So between these, it has a dual nature. Now, what that means is it is both a wave and a particle at the same time. A little bit out there when it comes to thinking about these things, but we're just going to keep that in focus. The nice thing for you, and at school level and even beyond, is we're never going to do anything where I expect you to remember both. So we're either going to deal with it as a wave or we're going to deal with it as a particle. But we're not going to combine the two because it's actually quite a difficult concept. And it's a little hard to get your head around that one. Okay, so that's one of the special properties. Another special property of light is it doesn't need a medium. Now, how do we know that? Now, we've discussed the fact that sound definitely needs a medium. I have to have something, otherwise I can't hear. But what about light? Our main source of light comes from the sun. The sun is thousands of kilometers away from us in space, in a vacuum, essentially. Space isn't 100% vacuum because there are particles in space. There's planets and stars and all the rest of it. But the sun is in a vacuum, essentially. The sun has its little chemical reactions happening. It's fusion and all sorts of things. It's a nice big nuclear explosion. We're thousands of kilometers away, but as the Earth turns towards the sun for us, where we are on the planet, we experience light. How does that light get to us? There's no medium, which tells us light doesn't need a medium. Light can travel through a vacuum. But this is what makes light really, really special. Light can travel through a vacuum and it can travel through substances, which is a good thing for us, because if light couldn't travel through a medium, light would hit our atmosphere and stop. Then we would still be in the dark. So we're very grateful that light has this wonderful property that it doesn't need a medium, okay? Now, the last nice part about light is that it's part of the electromagnetic radiation. Throughout this series, just to make life a little bit easier, we're going to use EM as a little bit of an abbreviation. It's simply to make our life easier when we write things down. Why is this nice for us, that light is part of the electromagnetic radiation spectrum? Because we cannot see the beginning of the electromagnetic radiation where we have very long waves, and we can't see the other end where we have very short waves, because we just can't. It's just not physically possible for us to actually see them. We're not designed that way. But we know that light's part of that spectrum, which means any experiments we do with light, anything that we discover about the properties of light, the things light does, we can then say, well, you know what? If light has this property, such as being a wave or a particle, then so does every part of the electromagnetic spectrum. And that's great for us, because then it makes it easier for us to decide on the properties of the electromagnetic spectrum and what it means for us in reality. Okay? Lots to take in. Let's talk about the wave-like nature. We've already spoken a little bit about this. When electromagnetic radiation is formed, it comes from two places, and it's a very, very special wave. Inside the sun, we have a chemical reaction happening. And in fact, it's a nuclear reaction, like with a nuclear bomb. So we have these tiny, minute hydrogen and helium particles that are decaying. They are exploding. Because they're exploding, they are creating charged particles that are moving. Those charged particles create an electric field around them because they are charged. Electric fields come from charged particles. Those charged particles are moving, but we also know, and we're going to deal this a little bit more in electricity, so you're just going to have to bear with me. When a charged particle moves, it also creates a magnetic field. There's a very, very close relationship between electric fields and magnetic fields, okay? So this is why we call this electromagnetic radiation, because it's both electric in nature and magnetic in nature. So it's a little bit of a strange concept. So what I'm going to do now is I'm going to show you an animation, because we can't show you a video because you can't see it. So I'm going to show you an animation, and we're going to talk about where we get this wave nature from, okay? So on this animation, and it's going to go quite quick, but I want you to watch it. You're going to see two parts to it. You're going to see a blue line and you're going to see a red line. So if we play it, now if you look at that, watch, I'm going to stop it there just quickly. What we have there is the red part of the line that you're seeing is the wave that's created because the particle's moving. So the particle moves up and down. As the particle moves up and down, remember from transverse waves, it's a moving motion, so it creates this transverse wave. Okay, so it's creating my crest and my shaft. But electric fields, okay, so this is my electric field that's moving. Electric fields have the special ability to create magnetic fields, and those magnetic fields move perpendicular, so they go at right angles to each other. Okay, so what we have is as the electric field is formed, a magnetic field is formed at the same time. And if we carry on to watch, it's gone through the rest position and it gets through to that point. Now, there we see, this is a 3D animation, which is great because it's exactly what you've seen. The red line, if you look at it, is a great transverse wave. And at the same time, we have the blue magnetic field. So let's just look at that again, because it does go rather quickly. Okay, and we can see that as one gets formed, the other gets formed. And it's a really great 3D animation. Let's look at this in a little more detail. We've broken it down into different points. I'm just going to remind you of what we said. So what we have here is, the charged particle would start at that point. My charged particle moves up, and as it moves up, this electric field gets made, which we would represent with an E. At the same time, because the electric field is made, my magnetic field is made. That's this, which is a B. That's a new symbol for you guys. You haven't seen that one before. We're not going to do calculations with it, but just so you remember that that means magnetic field. Okay? And let's just remind you what the E means, because you haven't seen that one before either. Now, the motion of this charged particle is continuous. It's going to go up and down and up and down and up and down, because it's a reaction that's happening inside the sun or whatever we're doing. So here we have it. It's gone a little bit further, and once again, as my electric field gets bigger and bigger and bigger and then smaller and smaller and smaller, at the same time, the magnetic field does exactly the same thing. And they're going to get to their crest at the same time, the peaks here and here. That happens at exactly the same time. It will also be the same size. So what I'm saying to you is that distance and that distance is the same. They're identical in every way, until eventually we get that beautiful wave that we can see that it's now been turned at right angles, and my blue part is coming out towards me and then away from me, and out towards me and away from me, where we get the crest and the trough from the light. This shows you, especially here, this diagram shows you so nicely, we have a transverse wave. Crests and troughs. Okay, wavelength, you remember all those definitions that we've done before. Okay, we get amplitude, which also means that these waves have frequency and they have period. So we've now realized that we are making a very, 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 very special transverse wave. They come in twos. Light is this. It is a pair of transverse waves that come at right angles at each other. Okay? This is one of the things that make electromagnetic radiation so, so special. Because it comes in pairs, we're able to actually stop one from moving and still have the other, or we can, depending, and that's what polarization does. We'll discuss that in grade 11 and 12. But this is also why we don't need a medium, because the energy that's moving is electric and magnetic. It doesn't need a medium to move through it. Okay? Quite a difficult thing to get into our heads. But why is this important for us? Because scientists have realized that this wave comes in packets. So it's not like a water wave where you have a little bit and some have a certain, sometimes you get them in a certain energy and sometimes you don't. And Oh, it's very random. This comes in packets. So what that means is we get what we call a photon. Now, a photon is a packet of light or a quantum of light. Quantum is a very important word here. Quantum simply means that it comes in specific values, okay? So what scientists have realized is, though the packets can be different sizes depending on what part of the what light we're looking at, whether it's red light, green light, blue light, ultraviolet, infrared, whatever the case may be. But it comes in a very specific pattern. So you'll always find these packets arriving together. Okay? So as it travels through the wave, we get them in packets as a specific value. We're going to talk about photons quite often. Okay? Photons are an interesting little concept. I'm hoping you've heard the word before. In some when you're looking at science fiction again, because they love to go into space, they'll talk about them having phototubes or photon rays or something like that. They're really talking about shooting light at something like a laser. Okay, lasers are great for that. Okay, we've discussed that we have a wave and how it's made, but that means for us that the wave equation is still valid. Okay, my wave equation still very, very valid. V equals frequency times lambda or lambda times frequency. However, when we're talking about the electromagnetic spectrum, specifically with light, this velocity is a very specific value, and it's 3 times 10 to the 8, unless you are told otherwise. But that also means it has a very specific symbol. It is a C. Okay? So when we're looking at equations that require using the wave equation, V equals F times lambda, frequency times wavelength, we actually need to use the velocity of light or the electromagnetic spectrum work in that velocity, and that's C. So let's quickly look at an example. Okay? It says to you, calculate the frequency of an electromagnetic wave with a wavelength of 400 nanometers. Just a quick reminder here, nanometers means that you have 10 to the minus 9 meters. Remember, wavelength must be measured in meters. You can't keep it in nanometers, it's not its SI unit. Let's write down what we know and what we're required. Frequency is what we're asked for. They give you wavelength, which is 400 nanometers, but I can't use it like that. We need to make it meters, so we're just going to times 10 to the minus 9. And now you're probably all going, oh wait, hang on. They want frequency and don't have speed, but they say to you that it's an electromagnetic wave. In fact, this is light because of the wavelength. That means I need to know that C is 3 times 10 to the 8. Okay? This is considered knowledge that you know. It is inferred in the question. So they're not always going to tell you directly what the velocity is, okay? Now, with all of that information, I'm hoping you're all going, we can do that. We've seen questions like this before. Of course you have. C equals F times lambda. C is 3 times 10 to the 8. Frequency is what I'm looking for. And now we have 400 times 10 to the minus 9. In this section of work, you're going to often have to use scientific notation on your calculators. Please make sure you know how to use your calculators properly with how you put the scientific notation in, because that's the biggest problem. Is if you do it wrong, you often get an answer that has too many zeros or doesn't have enough. 3 times 10 to the 8. We're going to divide both sides by 400 times 10 to the minus 9, and we get a ridiculous answer of 7,5 times 10 to the 14 hertz. Huge, huge frequency. This is a tiny, tiny, tiny wave, okay? I can't even make the distance small enough for you to see. So it's a tiny, tiny wave going at an extremely high frequency, okay, which means there's lots of them per second, and it's going really, really fast. Okay, ready for another one? And then we'll take a break. Let's do one more. What is the wavelength? Wavelength of a photon of light, giving you a hint, with a frequency of 101,3 kilohertz. Okay, frequency 101,3 kilohertz. First of all, I can't use kilohertz. Not a chance. Okay? Now you're probably saying, but how do I know how to convert it? Well, think about the fact that if I go from meters to kilometers, I would times by 1,000 times 10 to the 3. Kilo, the K, is times 10 to the 3 as a conversion, which means this is 101,3 times 10 to the 3 hertz. Great. Once again, you're looking at this question going, oh, hang on, no velocity. But your hint, photon of light. That means I know the speed is 3 times 10 to the 8 meters per second. Okay? Great. So, C equals F times lambda. C is 3 times 10 to the 8. My frequency is 101,3 times 10 to the 3. And we're going, oh, we can do this. We've done lights. So this is 3 times 10 to the 8 divided by 101,3 times 10 to the 3. And you get 2961,5 meters. This is a very, very long wave. Okay, this is probably a radio wave. Very, very, very. This is a wave that has a wavelength of over 2 kilometers. That's huge. Okay, so it's a bit of an unusual question. 2 kilometers. Okay, now lots for you to take in, especially for you to think about with the waves and the two waves moving together. So we're going to take a short break, stretch your legs, get something to drink. When you come back, we're going to look at the electromagnetic spectrum in a little more detail. So we'll see you in a couple of minutes. Welcome back, and like I said before, into the break, we're now going to look at the electromagnetic spectrum, and this is going to be lots of fun. Now guys, when you do the spectrum, it's really important that you understand the way the spectrum works and you know the different parts of the spectrum. You don't have to know specific values to the spectrum, but you do need to know how the spectrum works and where it goes from. Now, I'm hoping you all have some sort of diagram of the spectrum, and I have one on the screen where I'll show you which shows you the basic parts of the spectrum. Starting from radio waves, which are quite long, low-frequency waves, and it moves all the way to gamma rays. So we look at radio waves, microwaves, infrared waves, visible waves, which is light, ultraviolet, X-ray, and gamma. Now, we're going to look at each of those in a little more detail. I'm going to give you values for frequency and wavelength, but the honest truth is, grade 10s, is that they're an indication of where they stop and start, but the boundaries aren't exact. So it's not like I'm going to go from radio waves, and as soon as the wave changes from 10 to the 8 hertz to, 10 to the 7 hertz to 10 to the 8 hertz, it's now becoming a microwave. There's a little bit of a fuzzy, it's like looking at a rainbow where the colors just sort of blend into each other. It's the same concept, okay? So what we're going to do is we're going to look at the electromagnetic spectrum, and we're going to do it in bits and pieces, and you're going to need to just stay with me, okay? So if we look at the electromagnetic spectrum, the first thing we're going to look at in the spectrum is the fact that we have a whole bunch of things. I'm just going to go back a little bit. And the electromagnetic spectrum is made up of 7 distinct points, okay? We have radio waves, microwaves, infrared waves, visible light, ultraviolet, X-ray, and gamma rays. Let's now think about, we're going to start at the beginning, and we're going to look at radio waves, okay? Now, radio waves do exactly what they say they do. That's what's responsible for us being able to hear radio, okay? They're very long wavelengths, so it's the very first part of the spectrum. They're very long, okay? Those radio waves have high, big wavelength, short frequency. So if we look at a radio, which is a good example of one, their wavelength is between 1,000 meters and 0.1 meters. That's a kilometer to about 10 centimeters. Their frequency, though, is very low, in relationship to the rest of the spectrum. I still know 10 to the 6 hertz is very high, so is 10 to the 10, but it's actually quite low once you get to the rest of the spectrum. And those are the waves that are responsible for us hearing radio, okay? Not only that, but once we get past the fact that we use them for radio, so radio waves are used for all sorts of things, okay? Now, one of them is for very, very, very big telescopes. In fact, the SKA, the Square Kilometre Array, which South Africa is still bidding for and hopefully we get, is a whole bunch of telescopes that look at the world outside, look at the stars in the universe, and pick up radio waves that are being transmitted from stars and all sorts of other celestial bodies from far, far away. And these telescopes are extremely big. They have big, big dishes. Those dishes then are able to pick up these radio waves and they translate that into images that we then make, which is actually really nice. So we use these huge, big telescopes. Another example of one, which is they're just ginormous, these big plates. It's almost looking like a satellite dish like you use at home in order to get your DSTV. Okay, so we use radio waves all sorts of places, specifically for looking at the universe out there. The next part of the spectrum is microwaves, okay? Microwaves come after our radio waves, so there they are. They have a slightly shorter wavelength, slightly higher frequency, and I know you're all going, oh, we know microwaves. Of course you do. Microwaves are used for cooking. So we love microwaves because it's a good place for us to cook. So there we go as an example of what microwaves are. They range in size now between 15 centimeters and 0.1 centimeters, so they're getting much shorter. But look at the increase in frequency. They go from 10 to the 10 hertz to 10 to the 12 hertz. That's quite a big difference from radio waves, which started at 10 to the 6. So microwaves we use for cooking, for all of that sort of stuff, which means they're also slightly hotter when it comes to the heat they produce, okay? Microwaves are starting to become a little more dangerous for us. You all know that when they cook food, they're actually heating up the food. They excite the molecules inside the food, and we get that's what makes it nice and hot. A klystron, which is the diagram you can see on the screen at the moment, this is a very special little, it's not very little, it's quite a big piece of equipment which is used to produce microwaves in industry when they need to use it for experimentation and that sort of stuff, okay? We don't want to have one of those running around at home because it can get quite dangerous, so we'll ignore those. Microwaves are also responsible for satellites and that sort of stuff, so we use them in all sorts of different environments, and it's very important for us. The next wave we're going to look at is infrared. Infrared, you're going, oh wait, no, we've heard that term before. Of course you have. Okay, in fact, often you'll see infrared imaging. Infrared imaging is when you see those wonderful images and you see a person and they look like they're red and blue and yellow and green and all sorts of things. It shows the heat that a body produces. Every single body in the universe, every object produces a certain amount of heat. Sometimes that's quite significant, sometimes it's not. It all depends on what it is. Your lights at home would be producing a lot of heat. Your body produces a lot of heat, so that's why we can see people when it's infrared. It's a nice, interesting thing to use. We can't see infrared, okay? It's not something we can physically see with our eyes, so we use special equipment for that, okay? So with infrared, we notice that we're starting to get, in fact, there's a very nice image showing you infrared. The red parts in the image are where this person is hotter, okay? His head, it's blue, it's not quite so hot. Now the wavelength is now changing from 10 to the minus 3 to 10 to the minus 6 meters. Now they're getting really, really small. The frequency, 10 to the 12 hertz to 10 to the 15 hertz. Much, much larger, okay? It's an approximation. Getting much, much bigger. So it makes it a lot easier for us to see the difference. And I'm hoping what you're noticing here, grade 10s, is as the wavelength is getting smaller, the frequency is getting higher, okay? So as the wavelength decreases, the frequency increases, and we're quite excited about that because we've seen a nice change. Now, what you're going to see is, and I'll show you, and you can see it on the graphic that I've got at the moment, is that as the wavelength gets smaller, you can see they're getting closer and closer together, the frequency is increasing. That's a very, very important relationship for you to get, grade 10s, because in terms of the spectrum, we can either have the spectrum in terms of increasing wavelength or increasing frequency, so be very careful when you look at that. The further along we go, the more we realize short wavelength, high frequency. The next part of the spectrum that we're going to look at when we get there is the visible light spectrum. So here we have visible light that ranges in our nice little rainbow: red, orange, yellow, green, blue, indigo, violet. Okay, rainbows are always in that order. There is absolutely there's no exception to that ever. And an interesting little fact for you is Sir Isaac Newton, when he's accredited with finding our rainbow and deciding what the colors are and being the first one to be able to disperse light into the rainbow, he couldn't actually ever see all 7 colors. He couldn't physically see all 7. He wasn't able to distinguish them, and it's actually really hard in the blue, indigo, violet section to distinguish them. But he knew there would be 7 because of what he believed in, and that was just what he decided, was that there would definitely be 7 colors, which is actually quite incredible if you think about it, that he knew that there would be 7 colors to the rainbow. And we will never know why he knew that, but he did. So we're quite excited. Of course, now we can prove that. Let's go on to UV light. Now, UV light becomes a very short wave, high frequency. UV light is extremely dangerous for us, okay? This is what causes skin cancer. UV light, and you're going to see in a second, and I just love this graphic because this is a plant under UV light. It's quite interesting. Its wavelength ranges from 10 to the minus 7 to 10 to the minus 8, very, very short. 10 to the 16 to the 10 to 17 hertz as its frequency, and UV lights are often used in clubs and at concerts and stuff, and I'm sure you've all been in UV light. We also call it black light in theatre, where if you have white on or anything like that, it glows in the dark, and it's actually quite interesting to see. It's because of the interaction of the light and the colors and the chemicals in the clothes and stuff that you're wearing. So here, this is actually a plant that's been shown under UV light, and you can see the different colors that you get, and it's actually quite fun to watch. UV light can be used for all sorts of things, and in fact, UV light is split into 3 categories: UVA, UVB, UVC. Now, these 3 variations of UV light are the things that are responsible for ozone and that sort of thing. We'll come back to that in a second. What else we use UV light for is when we look at scientists. I'm sure you've all watched CSI, you've watched those programs, and they spray something on the wall, and they go, oh, I wonder if there's blood. They spray something, and out comes the UV light, and then you see it glow. Okay, it's luminescent. It glows in the UV light. That's a very important usage of it. Another use of it is when shop owners scan money. There is a ultraviolet strip put into our money to stop people from forging it. That's important because we know forged money is a very bad thing. So every currency in the world has these, and that's often shop owners will have those little machines that they'll scan their money in. And recently, in the about a year ago, there was a whole scam about the 200 Rand notes because they were becoming quite easy to forge. And for a long time, shop owners wouldn't take 200 Rand notes because they were being forged. Okay? And if you got one, it was a bit too bad because you were hoping the bank wouldn't give you one. But they scan it under a UV light to check that it's actually a genuine note. So when it's scanned, it glows in the dark. That is an example of where we're using the fact that something will glow in the dark for a chemical test, okay, where we use UV light. Nice way to test for stuff. It's quite interesting when we look at the forensic world. Next part of our spectrum is X-rays. I am hoping that none of you have had to have an X-ray. I have. It's not that painful, but at some stage we might. X-rays can be quite dangerous, though. They have a very, very small wavelength between 10 to the minus 8 and 10 to the minus 11, and high frequency, 10 to the 17 to 10 to 21. I'm not 100% sure what this is an X-ray of, but it looks like it's a series of legs, okay, where you can see people have had pins put in their legs, and you can actually see where they are. The point of an X-ray is that it is able to penetrate the human body. So it can go through flesh and organs, and then it gets absorbed by or reflected off bones and hard objects inside the body, which is why we get this white part. It's reflected back off a plate, which then takes a photograph, essentially. It is very, very dangerous. And in fact, if you're pregnant, for the girls, you're not allowed to have x-rays because it can damage your baby, so we don't want to do that, okay? You also don't want to be living in an x-ray. In fact, if you've ever gone for an x-ray, you'll know that the technician who takes the x-ray sits in a little cubicle, shielded, and she actually has, or he has lead shielding, so that he doesn't get it, or they don't get affected by the x-ray, because long-term exposure can be very, very bad for you. We're going to show you another x-ray in a second. Of course, we can take x-rays of all sorts of parts of the body, and they show us it's what they use for clean breaks. This looks like a dental x-ray, I think. It's a person's head, so when you go to the dentist and they take x-rays of your mouth, it's for them to be able to see what's happening with your teeth. As you guys get older, you'll realize that your wisdom teeth can become a problem. Your dentist will take x-rays of your teeth to see when your wisdom teeth are coming out, if they are coming out, and if they need to actually be removed, which we don't want ever to happen because it's not fun. Okay, so we have x-rays. This one is of dentals. It's showing the teeth quite clearly in your x-rays. X-rays we use at airports, go through x-rays machines. They go and x-ray your bags, and you have to take your laptops out and your iPads, and you have to put your phones on things, and it gets very exciting. It gets very annoying after a while. Actually, last part of the spectrum, gamma rays. Now, gamma rays are extremely dangerous. Very high frequency, very low, very, very small wavelengths. So we have our gamma rays range between 10 to the minus 11, 10 to the minus 15, and 10 to the 21 hertz, 10 to the 24 hertz for frequency. That is extremely high, okay? Now, what that means is gamma rays are very, very dangerous. Gamma rays, if you're exposed to them enough, can kill you. Now you're going, oh, but we get them from the sun. Yes, we do, but we don't get them in concentrated bursts. Okay, so we're not exposed to them like we would be if we're looking at something that's nuclear or radioactive. So gamma rays really come from inside our nucleus of an atom, and inside that nucleus a reaction happens and it spits out a particle which gives us gamma radiation. It's a little difficult to see, but if you watch on the screen you can see that we have an electron. It's an atom that's getting excited, and what's happening is it's shooting off bits of gamma rays. That's what you can see on the screen, the wave that's coming off, that's the gamma ray. Gamma rays are dangerous, but we can use gamma rays to do things like sterilize medical equipment because it kills bacteria. It'll be gone, okay? Which is a good thing. We like it to be gone. We don't want the gamma rays, okay? Because then we don't want the bacteria on our sterilized equipment, sorry, so we use the gamma rays to get rid of it. But we need to make sure we are protected from the gamma rays, okay? Why is this important to us? Because when we look at our spectrum, when we go back to our diagram, the smaller the wavelength here, the more dangerous they become. And in fact, what we say is, remember we said earlier that light can behave as both a wave and a particle. What scientists have realized is that when we have very long wavelengths, like the radio waves, these waves tend to behave more, oh, and we've got that in double, let's try not make that in two different colors. They have a wave nature, all of these. They behave like a particle sometimes, but not very often. So we're not going to find them doing the same sort of thing as particles would do, just because they're very, very long. When we get to the other end of the spectrum and we start looking at ultraviolet, X-rays, gamma rays, these tend to have more of a particle nature. So they tend to behave more like particles because of their high frequency. That means they're able to do more damage. Gamma rays, when these gamma rays come in contact with the human body, for example, because they're behaving like particles, those particles do damage to our cells and the nucleus of our cells and all sorts of things, and they start to erode them. Very, very dangerous for us, okay? We don't like that idea. That also means when we're talking about things like getting sunburnt, that whole ultraviolet radiation issue, okay? And if you've been listening if you watch TV, listen to the radio, people often talk about the fact that we need to be using sunblock, we need to be protecting ourselves. Of course we do, because ultraviolet radiation is extremely dangerous for us. Ultraviolet radiation actually has 3 parts. We're going to look at this now in a second. And because it can act like a particle, there are parts of ultraviolet radiation that actually penetrate our skin and start to damage our skin. Okay? So let's actually look at that, shall we? Ultraviolet light gets separated into 3 parts: UVA, UVB, UVC. You don't often hear about UVC though, but let's look at it. Now, when we look at these 3 parts of the ultraviolet radiation, they all come from the sun. That doesn't change, okay? UVC is very special because it can be absorbed by the ozone. So we have a picture of the dermis. UVB comes along, gets through the ozone layer, and can penetrate just the top layer of our skin. That eventually tans us. UVA goes all the way through the dermis to the bottom layers. When it gets to those bottom layers, that's where it starts to do damage, okay? That is where it starts to cause things like skin cancer, all right? So UVC gets absorbed by the ozone, and we need it to be absorbed by the ozone, so we want to make sure our ozone's there. UVB comes just the top layer. It's UVB that makes us go brown, or darker as the case may be. Or if you, like me, no, just red, okay? I cannot go brown. I do not have that ability. UVA is what penetrates the skin, goes through past all the skin layers, and that's where we start to get skin cancer and skin damage, which is obviously what we need to prevent. That means ultraviolet light has the ability to penetrate the skin. Ultraviolet light comes before X-rays. X-rays have a higher frequency, which means they can penetrate even more. And we saw that in the diagram, because with X-rays, they can penetrate the skin completely, and the organs, and everything else, and we get diagrams and pictures of the bones, okay? Gamma rays can go all the way through you. They're brilliant. They can penetrate just about anything, okay? So that is, what that shows me is the higher the frequency, the better its penetrating ability. Okay, lots for you to have taken in today. Let's look at a quick question. We're not going to spend too much time actually answering this because we could be here till Christmas, but this is the type of question you need to be able to answer. Says to you, give an example of the use of each type of electromagnetic radiation. First one is gamma rays, which we started with we ended with gamma rays, so we're going the other way around. Gamma rays, of course, are used in medical equipment to sterilize medical equipment. X-rays, used to image bones and to take pictures of bone structures and to know if somebody's got a broken bone, that sort of thing. Ultraviolet light, used in forensic situations. We used to know if there's been blood splattered or that sort of thing. Infrared, sorry, I missed out visible light. Visible light, well, we need visible light to see the world around us. Nice and simple. Infrared, used to see images according to their heat signatures. So places where we can't necessarily see something because it's too dark. All right, so it's nice for things like night vision goggles. Okay, so the military has use for those. Microwaves, to cook our food. Cell phones. Radio and TV waves, which fit in the same category. Listening to the radio, getting television signals, all of those sort of things. Nice and easy. All right. We have already spoken about the penetrating ability of our UV radiation, X-rays, and gamma rays. Remember, the higher the frequency, the more likely they are to penetrate. Okay. Now, question 4. Says to you, indicate the penetrating ability of the different kinds of EM radiation and relate it to the energy of the radiation. What that means is, what I'm wanting here is you don't need to go, well, radio waves have a high, you don't need to go through all of them, but this is where we need to get. Radio waves have a long wavelength and a high frequency. sorry, low frequency. That's the other way around. I'm hoping you all realize that. So it's a long wavelength and a low frequency. That means they have a small amount of energy. We're going to talk about where we calculate the energy in the next, after we've taken a small break, okay? That means small penetrating ability, okay? Radio waves get absorbed quite easily by mountains and all sorts of things. It's also why you sometimes struggle to find cell phone reception, okay? Because your microwaves have very bad, don't penetrate as well as X-rays and gamma rays, and you'll know that if you're driving somewhere and you go through a valley, sometimes you really struggle to pick up your cell phone, okay? Or at home, if there's lots of buildings around you, you can sometimes struggle to pick up a cell phone signal. It's because it has a very small penetrating ability. So it's not going to travel through buildings and that sort of thing, and radio waves don't generally do that. However, we get to the other end of the spectrum where now we're looking at our gamma rays. Okay, they have a very short wavelength and a very high frequency. Let's change it so that it doesn't look like that's one word. They have a high frequency, which means they have a very high energy. And that high energy gives it a big or a great or a large penetrating ability. And essentially, a good way to remember this is frequency and energy are very closely related to each other. So if a wave has a very high frequency, it has a high penetrating ability. If it has a very low frequency, then it has a very small penetrating ability. Okay? Last one for now. Why do we need to protect ourselves from ultraviolet radiation from the sun? Sounds like a bit of a stupid question, doesn't it? But you know what? The whole point of your science curriculum, and this is what makes it so nice, is we want to put what you're learning in the classroom into context for you, and for it to be something that you can take out into the real world. This is a big thing. Ultraviolet radiation is so bad for us, okay? Nothing wrong with getting a tan, okay? Really nothing wrong with it, and it's important that we do see the sun. We need to get vitamin D from the sun. But when we are overexposed to ultraviolet radiation, because remember UVA can penetrate the skin, it can cause skin cancer and other skin-related diseases. It also can cause premature aging, so it makes you look older than you actually are. And I know as teenagers you go, oh, that would be wonderful. But you know, as you get older, you don't want that. You don't want to be looking like you're 60 when you're only 40, okay? Just isn't cool. But the point is we need to protect ourselves. And we do that by using sunblock, sun cream, and UV protective clothing. Okay, making sure that our clothing can help us as well. Because it doesn't help us if we dressed like an Eskimo, but actually the sun can go straight through it. Okay? We need to protect ourselves from it. That also remember, guys, that means even on a windy day or a cloudy day, you can still get burnt from the sun if you're near water or on sand, because the sun reflects off it. Okay, very, very important. Now, wow, we've done a lot of work in this last session. So, we're going to take a short break, and then when you come back, we're going to look at the calculations that we need to work with for electromagnetic radiation. So get up, get a glass of water, we'll see you in a couple of minutes. Okay, welcome back. Ready for that last stretch. Now, before we took a break, we were talking about the penetrating ability of electromagnetic radiation, which means we were looking at the fact that electromagnetic radiation acts as a particle. In grade 11 and 12, you're going to do a very important experiment called the photoelectric effect, where we actually prove that light and EM radiation has this particle nature, where we have these little particles of light that come along and they knock electrons off a metal surface. But when we look at that and we go, well, how does it do that? How can we measure it? We're going to come back to that whole concept of the fact that when we started today, we said that light is actually a photon. We can think of a photon as well as being a quantity of energy, as being a little packet of light that is like a little particle that now moves along. So it comes in packets and shoots, like cricket balls out of a bowling machine, okay? It comes out all the time and we get these particles. Now, for example, the cricket bowling machine, you set the bowling machine to always spit out the cricket ball at a certain speed. It has a certain energy. You can also set up the bowling machine so that it can spit it out at a specific rate. That's its frequency. So what you have is you have these balls coming out the bowling machine at a specific speed, at a specific frequency. You've actually created an electromagnetic radiation wave. That's what you've done. You've got particles coming out. So it's almost like light, where you have these particles coming out at a certain speed and a certain frequency. That frequency gives my electromagnetic radiation energy. That's where the energy of the light comes from. And we can use that energy, and that energy can be measured. The energy that's measured has a very specific equation, which we're going to quickly look at, which says that the energy of a packet of light is h times f. But h is a specific value known as Planck's constant. And that is named after a very important scientist named Max Planck. He was a German scientist. He did a whole bunch of calculations. He did a whole bunch of experiments, which we can redo, which is why it's a constant. We know that it's a real value. And he got to the value that h, which is his constant, is 6,63 times 10 to the minus 34 joules seconds. It is extremely, extremely tiny. So what that means here is actually the energy of our photons is very, very small compared to other energies that we would look at. So we're not going to get light that has energies of 300 joules or 4,000 joules or anything to that effect. It's going to be very, very tiny. And in this section of work, my suggestion is that you put your calculators into scientific notation, because your answers are going to have exponents to them, okay? You're going to have to look at it. Now, 6,63 times 10 to the minus 34 will be given to you on your information sheets. It's joules seconds, not joules per second. Please don't put the minus 1 there. It's an easy mistake to make because we don't have a lot of units where we don't have a minus. You know, in velocity, it's meters per second, so it's ms minus 1. Acceleration is meters per second squared, so it's it's ms minus 2. Here, that's not the case. It's just joule seconds, J, S. Remember, it's a capital J because joules is named after a scientist whose surname was Joule, so it's a capital. But let's look at what all these little pieces mean. E is the energy of the photon, and it is measured in joules. H is Planck's constant, which we've just looked at. F is frequency. Same frequency we've done over and over again, and that's measured in hertz. But sometimes we aren't given the frequency of light. So we can actually manipulate the equation, and we get a second equation, which I've already written here, we've already got, which says that it's equal to c over lambda. But where does that actually come from? Remember, earlier today, we did the fact that the speed of light is frequency times lambda, which means frequency is the speed divided by wavelength. So I can take this c equals f lambda, and I can put it into this equation in place of f, which replaces it, so h times f becomes h times c over lambda, okay? Where now we remember that c is the speed of light, or the speed of any of the electromagnetic radiation, and it's meters per second, and lambda is wavelength, which must be measured in meters. Often in this section, we're looking at very small wavelengths. It's only really radio waves and microwaves that have wavelengths that we can do in terms of meters. The rest start to go into nanometers and micrometers. But remember, 1 nanometer is 1 times 10 to the minus 9 meters. You must have that conversion. Okay, let's put this into calculations because that's where we really learn how to use these equations. Here it says, how is the energy of a photon related to its frequency and its wavelength? Now you're going, well, what do they want? They don't want a calculation here, okay? This is not a question. I can't do a calculation because I don't have values. It's an explanation question. So they're saying to you, if I consider the wavelength of a wave, how does that affect energy? If I consider frequency, how does it affect its energy? So energy is HF. H is a constant. But now, if I had to increase the frequency of my wave, this value gets bigger. What would happen to the energy? And you go, well, H is a constant, it's not going to change, so I'm taking a set number, multiplying it by a bigger number, so my answer must be bigger, which means the energy increases. So how would we write this down? We would say that if we increase the frequency, that would mean that we increase the energy. Or vice versa. This tells me that frequency is directly proportional. Actually, we should put it the other way around. Energy is directly proportional. You all know this term. To frequency. I hope some of you are going, oh, but we could write this in as a mathematical equation. Of course we can. We can write it as E directly proportional to F. That's a great concept for us because what that actually means for us is, for example, if I double the frequency, I will double the energy. If I half the frequency, I half the energy. Directly proportional. What about wavelength? Well, E equals H times C over lambda. Remember, H and C are both constants. They're not going to change. Lambda is now part of a fraction. That means if lambda gets bigger, it's at the bottom of a fraction, which means my overall answer is going to get smaller. If lambda gets smaller, then my overall answer is going to get bigger. So this means for us that if we increase lambda, we are going to decrease the energy. Can you tell me what that means in terms of proportionality? Considering we said E and F are directly proportional, that means lambda, wavelength, and E have to be inversely proportional. So E is inversely proportional to wavelength. Okay? In other words, if I halve my wavelength, I will double my energy. If I double the wavelength, I will halve the energy. Okay? How do we write that as an equation? We can say that E is inversely proportional to 1 over wavelength. Okay? That is the relationship between energy and frequency, energy and wavelength. Very, very, very important relationship. Okay? You all got that? Great. Let's look at a question. Now we got to one where we're going to use values. We like those. So here we have, what is the energy of a photon with a frequency of 3 times 10 to the 8? We go, oh, we can do this. They want energy. They said frequency is 3 times 10 to the 8. We need H. H is a constant. Now, in a test or an exam, I like to write down my given information. You don't necessarily need to write down the constant h because it's on your information sheet. But sometimes I think it's important for you to write it down so you remind yourself what it looks like. Otherwise, you tend to get a little confused, but that's okay. Equation, I know frequency, I know h, brilliant. We go E equals h over f. Now, the only reason why I've written it below my list is because I'm going to run out of space because it's a big number. So it's 6,63 times 10 to the minus 34. H, we were given it in as a normal hertz, so it's 3 times 10 to the 8. And just, we do it on our calculators. Please, I'm begging grade 10s, learn how to use your calculators properly here, because often what you do, and I did say this earlier today, is when you put this into your calculator, you don't use your exponent button or the little button on your calculator that says times 10. You type in 6,63 and then you go times, proper times 10, exponent, or you go 10 and use your X power button. And what that does is you actually add in extra zeros, so it becomes a problem. So please be careful there. When we do this on our calculator, we get 1,99 times 10 to the minus 25 joules. And I told you earlier today already that this is tiny, small, small, small value, okay? That's what you must expect to get if you got a very big value. So in other words, even if you get a value of 1 joule, that is big for a photon, okay? Then you know you've made a mistake. Please go back and check it. You must have these, it's like a little person in the back of your head that rings a bell and goes, no, 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 there's a problem here. Tiny answer. Please be careful with your rounding off here as well, grade 10s. Okay, remember we round off to 2 decimal places. This is not an exact value on your calculator. It's 1,990 something, I think. So you've got to make sure you round off properly. Always to 2 decimal places here. Very, very important. Ready for another one? I think so. Now, what is the energy? Brilliant. E. Okay, we're right there. Of a photon of light with a wavelength of 660 nanometers. Okay, they're changing things up here a little. So, what do we know? Well, we're looking for E, and we were given the wavelength of 660 nanometers. Can I use it in nanometers? Of course not, because remember, nanometers is not an SI unit. We must change it to meters, and I already told you today that that means I've got to take the 660 and times by 10 to the minus 9. Now, we had 2 equations. We had E equals H times F, and we had one that said E equals H times C divided by wavelength. That's the equation I'm going to have to use this time. Because I don't have frequency, you are welcome to work out the frequency and then use the equation E equals HF. But if you make a mistake when you're working out the frequency, you will lose the marks for your final answer. And you don't want to do that because that's a stupid way to lose marks, okay? So we remember that C is a constant. It's the speed of light in a vacuum. H is 6,63 times 10 to the minus 34 joule seconds. We have 3 out of the 4 unknowns. We can put this into the equation. So I'm going to write the equation again. And we get 6,63 times 10 to the minus 34. C is 3 times 10 to the 8. My wavelength is 660 times 10 to the minus 9. On your calculators, you can work out the division first and then multiply by 6,63 times 10 to the minus 34. Or you can go 6,63 times 10 to the minus 34 times 3 times 10 to the 8 divided by 660 times 10 to the minus 9. Your calculators are actually quite clever. They set up to do your maths as it's written, okay? So they'll be fine with that. And what we get is we get 3,01 times 10 to the minus 19 joules. That's quite nice, okay? Nice, easy question. Ready for another one? Okay, let's look at another question. This one, slightly more complicated. It says to you, what is the energy of a photon of light with a wavelength, so one of 532 nanometers, and one with a frequency of 13 gigahertz, and another part to the question, which has the longer wavelength? Wow. This is not nice. Not because the maths is difficult, but because you have lots of things involved in this question. They're actually asking you three things. They are asking you, first of all, to calculate the energy of the photon for the light that's 532 nanometers. Then they're asking you to calculate the energy of the photon with a frequency of 13 gigahertz. Then they are asking you which one has the longer wavelength. Compare the wavelengths. That's three parts in one question. So we need to make sure that we're doing every section. Let's start with the first part, which was to find the energy of the photon of light with 532 nanometers. So that's the first part. So we're going to go, let's look at that. And you're saying to me, Tracy, we need to change this to meters. Of course we do. So it's to the minus 9. Now we want the energy of this photon. We have its wavelength. So I'm hoping you're saying to me, now well, we know which equation to use. We have two options, E equals HF, or we can use E equals HC over lambda. And we go, well, we have lambda, so I have to use E equals HC. Okay? We go, okay, we can do this. We're okay. And I've written it in a slightly different format to what you used to, so let me write it the way you see it. It's actually the same thing. There we go. H, you know by now, 6,63 times 10 to the minus 34. C is 3 times 10 to the 8. And lambda, 532 times 10 to the minus 9. We dump all of that into our calculator, which we love, and we make sure we have it in our tests and exams, and we get 3,74 times 10 to the minus 19. Oh, let's make that right. Times 10 to the minus 19 joules. First part answered. So we go, okay, fine. Here I've got what is the energy of the photon. I've worked that out. I'm going to cross it out in the question because then I know I've done it. Second part of the question. What is the energy of light with a frequency of 13 gigahertz? Okay, so I'm actually going to do this in another color so that it's easier to see. So now we know the frequency is 13 gigahertz. And we go, well, problem here, because actually I can't use gigahertz. That's not the SI unit. The SI unit is hertz. In the back of your mind, you've got to go, oh, how do I work this out? Well, actually gigahertz is times 10 to the 9. So this is 13 times 10 to the 9 hertz. This is huge. This is an extremely high frequency wave. Okay? Now, which equation do I use? I have the 2 equals HF equals HC over lambda. Well, I have F. Let's use the easy one. E equals HF, where H is 6,63 times 10 to the minus 34. Hopefully by now you know that. You don't even have to look it up anymore. 13 times 10 to the 9. And we get 8,62 times 10 to the minus 24 joules. Much smaller energy, though, than the one we just had. With the 532 nanometers, we got times 10 to the minus 19 joules. That's 100,000 times more energy than this. okay? 100,000 times more energy. That's huge, okay? And yet it's still a very, very, very tiny wave. This is a very high frequency wave. They're still moving extremely fast, okay? Now, if we look at the question, we go, I've done that one. But we're not done. Because now they say, which has the longer wavelength? And we go, okay, well, let's see. We know I have two waves. One that has a wavelength of 532 nanometers. And I'm going to write it in meters because it's going to be easier to compare a little bit later on. And then we have a second wave, which has a frequency of 13 gigahertz. There are two ways you could work this out. You could either go and work out the frequency of this wave and of the wavelength we know, and then compare it to the frequency of 13 gigahertz. But then we've got to remember, if it's a bigger wave, it must have a smaller wavelength, it must have a smaller frequency, and there we could get ourselves into a little bit of trouble. So let's do it the easy way. Let's take the fact that we know we have a frequency of 13 gigahertz, which is 13 times 10 to the 9 hertz, and work out what that wave's wavelength is. Okay, that's a much better way because it's much easier to compare wavelength to wavelength than frequency to frequency. So that's what we're going to do. We know that the speed of light is equal to frequency times wavelength. The speed of any electromagnetic radiation is 3 times 10 to the 8. We know this frequency is 13 times 10 to the 9. To get wavelength on its own, we're going to divide both sides by 13 times 10 to the 9. And here, I now get an answer of 2,31 times 10 to the minus 2 meters. That's the one wave, remember. The other wave that we had was 532 times 10 to the minus 9. Which one's bigger? Be careful here. The bigger the value of the minus in the exponent, the smaller the number, which means 532 times 10 to the minus 9 meters is much smaller than 231 times 10 to the minus 2 meters. So this is my bigger wave. This is my bigger wavelength, okay? How do you write that down? Because now I've calculated it. That's not enough, grade 10s. Because they asked you which one has the bigger wavelength, not just to calculate it. So what you need to do now is give your answer in words. So you say, therefore, the wave of frequency equal to 13 gigahertz has the bigger wavelength. Okay, be very careful here, grade 10s. As an educator, I see this quite often where I know that you've worked it out, but you actually haven't come to a conclusion. So please be careful because it's not your examiner's job when they mark to go, ooh, I think they knew the answer, so I'll give them the marks. In fact, they'll go, okay, you worked it out, but you didn't answer the question. And throwing away 1 or 2 marks every now and then in a test or an exam can add up to lots of marks by the time you're done, and you don't want to do that. Not for stupid things. You don't mind it if you lose a mark because you got the answer wrong, but when you lose a mark because you did something silly, then you need to be smacked. Okay, you need to kick in the bum for doing something stupid. Okay. Wow, we have done a lot of work today. So let's just quickly summarize this up before we say goodbye. We started by looking at light. Light has lots of very special properties, and we look at light because it's part of the electromagnetic radiation spectrum. Light, at the moment, the speed of light 3 times 10 to the 8 is considered the maximum speed limit of everything. And it's a constant, and any part of the EM radiation will travel at 3 times 10 to the 8. Light has both a wave nature and a particle nature, so it behaves as both, okay, and that makes it very important for us. The EM radiation has a nice spectrum, which is radio waves, microwaves, infrared, visible, ultraviolet, X-rays, and gamma rays. All 7. You need to know those. And we noticed that as we went across, the radio wave started at a long wavelength, small frequency, and as we got further along the spectrum till we got to gamma rays, the wavelength got shorter and shorter and shorter, and then the frequency got higher and higher. So as we increase frequency, we decrease wavelength, or as we decrease wavelength, we increase frequency. That happens because the speed at which they travel is constant. Okay? We then looked at the penetrating ability of our spectrum, and we realized that radio waves with their very long wavelength, very short frequency, don't penetrate, so they don't behave as much like a particle as gamma rays, which have a very high frequency, short wavelength, which have a very high penetrating ability, okay, which makes them very, very dangerous. We then talked about things like ultraviolet radiation and why we need to protect ourselves from the sun, realizing that UVA and UVB are very, very dangerous for us, and UVA can penetrate our skin, causing skin cancer, okay? So we looked at some of the dangers. Things that you need to now go home, need to be thinking about, which we didn't really cover, but it's something you can do as research because they could come up, is what are the dangers of us using our cell phones and the fact that they produce an electromagnetic radiation? All right, and it's become quite a big thing and a big discussion in scientific communities about whether using cell phones and having them by our ears all the time can cause brain cancer. There's some studies that say it can. It's been linked to it. Might be true, might not be true. It's a good thing to go and research. What about somebody working in the medical field who's exposed to X-rays all the time? What are the dangers they face? What are the things we need to do to prevent that? Okay, very important. These are things we need to be thinking through and discussing. Then we looked at electromagnetic radiation as a particle in particular. We talked about it being a photon coming in packets. We just saw Planck's constant, which is 6.63 times 10 to the minus 34 joule seconds, not joules per second. And then we've done some calculations where we've looked at the energy of a photon. If you now go back and just think, we said gamma rays have very high penetrating ability, which means they have a very high frequency. They have lots and lots of energy, equals HF. So that F value is very, very high for gamma rays. For radio waves, it's very, very low, comparatively speaking. That means it has less energy. That's why it doesn't penetrate. So the amount of energy the radio wave has determines how much it's going to penetrate, what damage it can do. Okay? You got that? We have done a lot of work today. Okay? Lots of things for you to think about, lots of stuff you need to study. Make sure you do that. This is now the last session of Wave, Sound and Light. We've covered all of it, and we're very excited. So in the next session, I'm not really you're going to be carrying on to another section, but that's it from me for now. So we'll see you in the next lesson. Goodbye.